Right now, roughly 238,900 miles above the surface of the Earth, a sphere of ancient rock is silently circling the planet at 2,288 miles per hour. It has been doing this for approximately 4.5 billion years. It has no atmosphere. It has no magnetic field. Its surface temperature swings from 260 degrees Fahrenheit in direct sunlight to negative 280 in shadow. Nothing lives there. Nothing has ever lived there. It is, by every measure of what we typically consider important, a dead world orbiting a living one. And yet, if it vanished tonight, if some impossible cosmic event simply erased it from existence between one heartbeat and the next, the consequences for every living thing on this planet would be so catastrophic, so far-reaching, so woven into the fundamental conditions that make Earth habitable, that within a few thousand years, you would not recognize the world you were born on. Within a few million, you might not recognize it as a place where complex life could survive at all. The moon does not merely hang in the sky. It holds the Earth together. It steadies the tilt that gives us seasons. It breaks the spin that gives us days. It pulls the oceans into rhythms that have governed biology since the first cell divided near a tidal pool. It shields us from the kind of chaotic climate oscillations that would make agriculture, civilization, and possibly even multicellular life impossible. It may have stirred the molten core that generates the magnetic field, keeping our atmosphere from being stripped away by the solar wind. And it did all of this so quietly, so constantly, for so long that we never think about it. You look at the moon and you see a nightlight. What you are actually looking at is the single most important object in the solar system for the existence of human life, and it is not even close. This is the story of what would happen if it disappeared. Not over millions of years, not gradually. Tonight, between one glance at the sky and the next. And what this thought experiment reveals is not merely a catalog of disasters. It is something far more unsettling and far more beautiful. It is the realization that almost everything you take for granted about the world, the length of your day, the stability of your climate, the rhythm of your oceans, the fact that seasons exist, the fact that the poles do not wander, the fact that the Earth's axis does not tumble like a spinning top, losing its balance, all of it, every single piece of it, depends on a dead rock that most people barely notice. Here is what would shatter everything you think you know about the moon, about the Earth, and about why you are alive at all to wonder about either one. If these deep explorations of the universe help you see the world a little differently, a like and subscribe truly helps this channel continue. It is that simple, and it means more than you know. Now settle in. This is going to be a long journey, and it begins with a question most people have never thought to ask. Are you ready? Let us begin. To understand what we would lose, we first need to understand what the moon actually is, how it got there, and what it has been doing to the Earth for the last 4.5 billion years. Because the moon is not just a companion, it is a relic of the most violent event in Earth's history. And the story of its birth is the story of why the Earth became the kind of planet that could eventually produce life at all. 4.5 billion years ago, the solar system was not the orderly place you see in textbook diagrams. It was a shooting gallery. Hundreds of protoplanets, some the size of Mars, some larger, careened through overlapping orbits in a disk of gas and dust surrounding the young sun. Collisions were not rare events. They were the primary mechanism by which planets formed. You did not grow into a planet by gently accumulating dust. You grew by smashing into other bodies at velocities measured in miles per second, absorbing their mass, and continuing on a slightly altered trajectory until the next impact. Earth, in this era, was already a substantial body, roughly 90% of its current mass, molten from the heat of accretion and radioactive decay, glowing dull red in the darkness of the inner solar system. It had no solid surface, it had no ocean, it had no atmosphere worth mentioning. It was a ball of magma orbiting a young star, and it was about to experience the single most consequential event in its entire history. The object that struck it has been given the name Theia, after the Greek Titaness, who was the mother of Selene, the goddess of the moon. Theia was approximately the size of Mars, roughly 4,000 miles in diameter, about 10% the mass of Earth. It had formed in roughly the same orbital region as Earth, probably near one of the Lagrange points where gravitational influences from the Sun and the proto-Earth created temporary islands of stability. But those islands were not stable forever. Gravitational perturbations from Jupiter, from other protoplanets, from the shifting mass distribution of the inner solar system itself, nudged Theia out of its safe harbor and sent it on a collision course with Earth. The impact was not a head-on strike. Most current models, particularly the canonical giant impact hypothesis refined by Robin Canup at the Southwest Research Institute, suggest that Theia struck the Earth at an oblique angle, roughly 45 degrees, at a velocity of approximately 9,000 miles per hour. To put that in perspective, this is about 2.5 miles per second. The energy released in the collision was on the order of 10 to the 32nd joules. This is a number so large it resists comprehension, but consider that the total energy output of every nuclear weapon ever detonated by humanity amounts to roughly 10 to the 18th joules. The Theia impact released approximately 100 trillion times more energy than the entire nuclear arsenal of the human species detonated simultaneously. The consequences were immediate and total. The impact vaporized a significant portion of both Earth's and Theia's mantles. It liquefied the rest. A plume of superheated silicate vapor, molten rock, and metallic debris was ejected into orbit around the Earth at velocities exceeding 22,000 miles per hour. The Earth itself was left as a ball of magma, thousands of degrees hotter than it had been moments before, spinning far faster than it does today. A day on the post-impact Earth lasted roughly 5 to 6 hours, with its rotational axis tilted by the off-center blow. The debris that was ejected did not fly off into space. Most of it remained gravitationally bound to the Earth, forming an immense ring of molten and vaporized rock, a disk extending tens of thousands of miles outward. And this disk, within a startlingly short time by geological standards, perhaps as little as a single year, according to simulations by Kokubo, Ida, and Makino published in 2000, coalesced into a single body, the Moon. Think about that for a moment. The Moon formed in approximately 1 year. The same object that has been shaping the tides, stabilizing the axis, and governing the rhythms of this planet for 4.5 billion years came into existence in less time than it takes the Earth to complete a single orbit around the Sun. It went from a ring of vaporized rock to a solid, spherical body, 2,160 miles in diameter, roughly 1/4 the size of Earth, in what amounts to an eye blink in cosmic terms. When it first formed, the Moon was not where you see it now. It was roughly 15,000 miles from the Earth's surface, about 16 times closer than its current distance of 238,900 miles. At that distance, it would have appeared enormous in the sky, perhaps 15 to 20 times larger in apparent diameter than it appears today. The tidal forces it exerted at that range were staggering. The early Earth's magma ocean, which covered the entire planet to a depth of hundreds of miles, was being pulled into bulges hundreds of feet high by the gravitational influence of this impossibly close companion. And then, slowly, over billions of years, the Moon began to move away. This is happening right now, today, and it has been measured with extraordinary precision. Between 1969 and 1972, the Apollo astronauts placed retroreflector arrays on the lunar surface, essentially mirrors designed to bounce laser beams back to Earth. By firing a laser from the McDonald Observatory in Texas, the Lick Observatory in California, or the Observatoire de la Côte d'Azur in France, and timing how long the light takes to return, scientists can measure the Earth-Moon distance to an accuracy of roughly 1 millimeter. The result of decades of these measurements, confirmed by the Apache Point Observatory Lunar Laser Ranging Operation, or APOLLO, is definitive. The Moon is currently receding from the Earth at a rate of 3.8 centimeters per year. That is approximately 1.5 inches, roughly the rate at which your fingernails grow. This number, 3.8 centimeters per year, might seem trivial. It is not. It is the visible signature of an immense energy transfer that has been reshaping the Earth for 4.5 billion years, and it is the key to understanding almost everything the Moon does for us, because the Moon is not just drifting away randomly. It is being pushed away by the very tidal interaction that makes it so essential. Here is how it works. The Moon's gravity pulls on the Earth's oceans, creating two tidal bulges, one on the side of the Earth facing the Moon, and one on the opposite side. But the Earth is rotating faster than the Moon orbits. A day is 24 hours. The Moon takes 27.3 days to complete one orbit. This means the Earth's rotation is constantly dragging those tidal bulges slightly ahead of the Moon's position. The bulge on the near side is pulled forward by the Earth's spin, so instead of pointing directly at the Moon, it points slightly ahead of it. That offset matters enormously. The gravitational pull of the slightly forward bulge tugs on the Moon, accelerating it in the direction of its orbit. When you accelerate an orbiting body, it moves to a higher orbit. This is the same principle that allows spacecraft to raise their orbits by firing their engines in the direction of travel. The Moon is being continuously, imperceptibly boosted to a higher orbit by the misaligned tidal bulge of the Earth's oceans. But energy is conserved. The energy that is being transferred to the Moon, pushing it outward, has to come from somewhere. It comes from the Earth's rotation. Every year that the Moon moves 3.8 centimeters farther away, the Earth's rotation slows down by approximately 2.3 milliseconds per century. This is measurable. It has been confirmed by studies of ancient coral growth rings, tidal rhythmites in sedimentary rocks, and eclipse records dating back to Babylonian astronomers in the 8th century BCE. A day on Earth is getting longer. It has been getting longer for 4.5 billion years, and the Moon is the reason. When the Moon first formed, 15,000 miles away, orbiting a planet spinning once every 5 to 6 hours, the tidal interaction was ferocious. The energy transfer was enormous. The Moon was receding far faster than 3.8 centimeters per year, and the Earth was decelerating far faster than 2.3 milliseconds per century. Over the first billion years, the Moon raced outward, and the Earth's day lengthened dramatically. The relationship has been slowing down ever since, approaching the gentle, almost imperceptible pace we measure today. This is the foundation you need. The Moon is not a passive ornament. It is locked in a gravitational dance with the Earth that has been transferring angular momentum from this planet to that one for longer than life has existed. It shaped the length of our days. It shaped the rhythm of our tides, and as we are about to discover, it shaped far more than that. Now imagine it is gone. Not in 1,000,000 years, not in 1,000. Tonight, between one breath and the next, the Moon simply ceases to exist. Every retroreflector, every footprint, every grain of regolith, every kilogram of its 7.35 times 10 to the 22nd kilograms of mass, gone, erased. The gravitational influence it has exerted on every molecule of water, every cubic meter of atmosphere, every wobble of the Earth's axis, severed. What happens first? The answer is not what most people expect. The first thing you would notice is not the missing tides. It is not the darkness. It is not the silence of a sky suddenly emptied of its most familiar companion. The first thing you would notice, the very first physical consequence of the moon's disappearance, is something you would feel in your feet. Or rather, something you would stop feeling. Right now, at this moment, the ground beneath you is rising and falling. Not because of an earthquake, because of the moon. The same tidal force that raises the oceans also deforms the solid body of the Earth. This is called the Earth tide, or the solid body tide, and it is happening continuously, everywhere on the planet's surface. The rock beneath your feet, the crust, the mantle, the entire solid Earth is being stretched and compressed by the moon's gravity in a cycle that follows the lunar day. The amplitude of this deformation is not trivial. At its peak, the solid surface of the Earth rises and falls by approximately 30 centimeters, roughly 1 foot, every 12 hours and 25 minutes. You do not feel this because it happens on a continental scale. Everything around you, every building, every tree, every mountain, is rising and falling together. There is no relative motion to detect, but sensitive instruments feel it. Gravimeters, devices that measure the local gravitational acceleration to an accuracy of 1 part in a billion, record the Earth tide with perfect clarity. It is a smooth, sinusoidal wave that has been pulsing through the planet since the moon formed. The moment the moon vanished, that wave would stop. Not gradually, not over days or weeks. Within hours, the tidal deformation would relax and the solid Earth would settle into a new equilibrium shape, very slightly more spherical, no longer elongated toward a companion that no longer exists. The effect on human perception would be zero. You would not feel the ground stop breathing, but every gravimeter on the planet would register it instantly. Every seismometer sensitive enough to detect long-period oscillations would record a sharp, unprecedented signal. The Earth relaxing, like a rubber ball that has been squeezed and suddenly released. The more dramatic consequences would follow within hours, and they would begin in the oceans. The tides as we know them are primarily driven by the moon. The sun also exerts a tidal force on the Earth, but its contribution is only about 46% as strong as the moon's. This might seem counterintuitive. The sun is 27 million times more massive than the moon. But tidal force depends not just on mass, but on the cube of the distance. The sun is 390 times farther from the Earth than the moon, and that distance penalty overwhelms the mass advantage. The moon, close and relatively massive for a satellite, dominates Earth's tidal regime. If the moon vanished, you would not lose all tides. You would lose the dominant component. Solar tides would remain, but they would be roughly 1/3 the height of the current combined tides. In practical terms, the average tidal range in open ocean, currently about 1 meter, would drop to approximately 35 centimeters. In coastal areas where tidal amplification occurs due to the shape of the coastline, the reduction would be even more dramatic. The Bay of Fundy in Nova Scotia, which currently experiences tidal ranges of up to 53 feet, the largest on Earth, would see its tides reduced to perhaps 15 to 18 feet. Still substantial, but a transformation of the coastline ecology that has existed there for millennia. The reduction in tidal range would begin immediately, but it would not happen smoothly. The current tidal system is a complex resonance. The moon's gravitational forcing excites natural oscillation modes of the ocean basins, and these resonances amplify the tides in specific locations. Removing the moon's forcing function would disrupt these resonances. The oceans would not simply settle into a calm, reduced tide state. They would slosh. The existing tidal bulges, two enormous accumulations of water positioned roughly in line with the moon, would no longer have a gravitational force maintaining their position. They would begin to redistribute under the influence of the Earth's rotation and the remaining solar gravity. This redistribution would manifest as a series of complex wave interactions spanning every ocean basin on the planet. Would this cause tsunamis? Not in the catastrophic sense. The tidal bulge in the open ocean is only about half a meter high, spread over thousands of miles. Its collapse would produce very long period, very low amplitude waves, detectable by ocean monitoring systems but not dangerous to coastlines. The more consequential change would be slower. Over weeks and months, the new tidal equilibrium would establish itself, and every coastline on Earth would find its tidal rhythms fundamentally and permanently altered. The ecological consequences of this change are difficult to overstate. Intertidal zones, the strips of coastline between high and low tide marks, are among the most biologically productive ecosystems on Earth. They are nurseries for hundreds of species of fish, crustaceans, and mollusks. They are feeding grounds for shorebirds. They are the interface between marine and terrestrial ecosystems, and their entire structure is governed by the rhythm and range of the tides. Reduce the tidal range by 2/3, and you do not simply shrink the intertidal zone. You collapse it. Species that depend on the daily exposure and submersion cycle, mussels, barnacles, anemones, limpets, crabs, sea stars, would find their habitat compressed into a thin ribbon a fraction of its former width. The competitive dynamics that maintain biodiversity in these zones would be disrupted entirely. Many species would face extinction, not because of any direct harm, but because the physical space in which they evolved to live would have effectively ceased to exist. Mangrove forests, which depend on tidal flushing to deliver nutrients and remove waste, would begin to decline. Salt marshes, which require regular tidal inundation to maintain the salinity gradients that support their unique plant communities, would dry out at their upper edges and become permanently submerged at their lower margins. Estuaries, the brackish mixing zones where rivers meet the sea, would find their salinity patterns fundamentally altered as the reduced tides failed to push salt water as far upstream. Coral spawning would be disrupted. Many coral species synchronize their annual mass spawning events with the full moon. The mechanism is not fully understood. It may involve moonlight intensity, tidal pressure changes, or both. But the correlation is well documented across multiple species and multiple ocean basins. Remove the moon, and you remove the trigger. The first spawning season after the moon's disappearance might proceed normally, driven by residual biological clocks. But within a few generations, the synchronization would begin to break down. Coral larvae, released at random times rather than in coordinated mass events, would face dramatically higher predation rates. Fertilization success would plummet. Reefs already stressed by warming oceans would lose one of their most fundamental reproductive strategies. The horseshoe crab, an animal that has survived essentially unchanged for 450 million years, spawns on beaches during the highest tides of the full and new moons. Reduce those tides, and the crabs cannot reach the upper beach where their eggs are safest from aquatic predators. The red knot, a migratory shorebird that travels 9,300 miles from the southern tip of South America to the Arctic, times its arrival at Delaware Bay to coincide exactly with horseshoe crab spawning season, feeding on the eggs to fuel the final leg of its journey. Remove the moon, collapse the spawning triggers, and you break a migratory chain that spans hemispheres. But the tidal disruption, as profound as it would be, is only the beginning. Because the moon does something to the Earth far more important than moving its oceans. It steadies the planet's spine. The Earth's axis of rotation is tilted at 23.44 degrees relative to the plane of its orbit around the Sun. This tilt is the reason seasons exist. When the northern hemisphere is tilted toward the Sun, it receives more direct sunlight and experiences summer. When it is tilted away, it receives less direct sunlight and experiences winter. The southern hemisphere experiences the opposite cycle simultaneously. This tilt, this specific angle of 23.44 degrees, is one of the most consequential numbers in the entire habitability equation of our planet. If the tilt were zero, there would be no seasons. The equator would receive maximum sunlight year-round. The poles would be permanently frozen, locked in eternal twilight. Weather patterns would be radically different. The temperature gradient between equator and poles would be steeper and more static, driving persistent, powerful wind systems with no seasonal variation. Agriculture as we know it would be impossible in much of the world. The vast temperate zones, the breadbaskets of civilization, would not exist. If the tilt were extreme, say 60 or 70 degrees like Uranus, the consequences would be equally dramatic, but in the opposite direction. Each hemisphere would spend half the year in nearly continuous sunlight and half in nearly continuous darkness. Summer temperatures would soar. Winter temperatures would plunge. The climate would oscillate between extremes that would make most of the planet's surface uninhabitable for complex life during significant portions of the year. The Earth's current tilt of 23.44 degrees sits in what planetary scientists sometimes call the Goldilocks zone of axial inclination, enough to create seasons that drive nutrient cycling, water distribution, and biological rhythms, but not so much that the planet swings between uninhabitable extremes. And the reason the tilt has stayed near this value, the reason it has not wandered chaotically over the last 4.5 billion years, is the moon. This is where the physics becomes extraordinary. The Earth is not a perfect sphere. It is an oblate spheroid. It bulges at the equator due to its rotation. The equatorial diameter is 7,926 miles. The polar diameter is 7,900 miles. That 26-mile difference creates a gravitational handle. The Sun and the other planets, particularly Jupiter, exert torques on that equatorial bulge, trying to pull it into alignment with the plane of the solar system. These torques, acting over millions of years, would cause the Earth's axis to precess, to wobble like a spinning top. And under certain conditions, that wobble could become chaotic. The axis could wander dramatically, flipping from a mild tilt to an extreme one and back again on timescales of millions to tens of millions of years. This is not theoretical speculation. It has been demonstrated mathematically. In 1993, Jacques Lascar, Frédéric Joutel, and Philippe Robutel at the Bureau des Longitudes in Paris published a landmark paper in the journal Nature showing that without the moon, the Earth's axial tilt would not remain near 23 degrees. It would undergo large chaotic oscillations ranging from 0 degrees to approximately 85 degrees over timescales of tens of millions of years. The planet would essentially tumble, its poles wandering across the sky, its seasons veering from non-existent to extreme and back again in a pattern that would be functionally unpredictable. The moon prevents this. Its gravitational influence on the Earth's equatorial bulge acts as a stabilizing torque, a cosmic gyroscope that keeps the axis locked within a narrow range. The current axial tilt varies between 22.1 and 24.5 degrees over a 41,000-year cycle known as obliquity oscillation. That is a range of less than 2.5 degrees. Without the moon, that range would be approximately 85 degrees. The moon reduces the Earth's axial instability by a factor of roughly 35. Think about what that means. Without the moon, the Earth's axis could tilt so far that the poles would point nearly at the sun for part of the year. The Arctic would experience temperatures above 100 degrees Fahrenheit during its summer months. The equator, tilted away from the sun during these extreme phases, would freeze. Ice sheets would advance from the equator toward the poles, the exact reverse of every ice age in Earth's actual history. Then, millions of years later, the axis would swing back, the poles would freeze again, the equator would burn, and the entire climate system would reorganize from scratch. No ecosystem could adapt to this. No species with a generation time longer than a few years could evolve quickly enough to track the changing conditions. The forests would die. The grasslands would die. The coral reefs would die. The large animals would die. The only organisms that might survive would be extremophiles, bacteria and archaea capable of tolerating enormous temperature swings. And even they would face extinction during the most extreme phases. Jacques Lascar's simulations showed that the chaotic zone for Earth's axial tilt without the moon was not a narrow band of instability. It was the dominant state. Without the moon, an Earth-like planet at Earth's distance from the sun would spend most of its time in chaotic axial oscillation. Stability, the kind of stability we currently enjoy, would be the exception, not the rule. A rare, lucky window, rather than a default condition. This is perhaps the single most important thing the moon does. More important than the tides, more important than the night sky, more important than the calendar or the poetry or the mythology. The moon keeps the Earth pointed in approximately the same direction, century after century, millennium after millennium, era after era. It allows the climate to remain stable enough for complex ecosystems to evolve. It allows seasons to recur predictably enough for biology to adapt to them. It allows ice ages to come and go within a narrow band of severity, rather than veering into planet-sterilizing extremes. And it has been doing this silently, without interruption, for 4.5 billion years. If the moon vanished tonight, the Earth's axis would not immediately begin to tumble. The timescale for chaotic obliquity oscillation is millions of years. For the first several thousand years after the moon's disappearance, the Earth's tilt would remain close to 23.44 degrees, drifting slowly as the gravitational perturbations from the Sun and Jupiter began to act on the unsupported equatorial bulge. You would not see the effects in your lifetime. Your grandchildren would not see them. But the trajectory would be set, the gyroscope would be gone, the slow tumble would have begun. And somewhere in the deep future, perhaps 10 million years from now, perhaps 50 million, the Earth's axis would cross a threshold into the chaotic zone, and the planet's climate would begin to oscillate with a violence that no complex ecosystem could survive. But between tonight and that distant catastrophe, there is another consequence of the moon's disappearance that would manifest on human timescales. A consequence that most people have never considered because they have never realized the moon is responsible for it. The darkness. The full moon reflects approximately 7% of the sunlight that strikes its surface. That number sounds small. 7%. A poor mirror. A dull reflector. And yet that 7%, bouncing off 14.6 million square miles of lunar surface, produces a luminance at the Earth's surface of approximately 0.25 lux during a full moon at zenith, a quarter of a lux. This is not enough to read by. It is not enough to cast sharp shadows, but it is enough to see. It is enough to walk through a forest without stumbling. It is enough to tell a predator from a shadow, a path from a ditch, a friend from a stranger. For most of human history and for most of the history of life on land, the full moon was the brightest source of light in the nighttime world. Remove it, and you remove the night light of the entire planet. The difference between a moonlit night and a moonless night is not subtle. It is the difference between navigable darkness and absolute blindness. On a clear, moonless night, far from artificial light, the only illumination comes from starlight, approximately 0.002 lux. That is more than 100 times dimmer than the full moon. It is so faint that the human eye, even fully dark adapted, can barely distinguish shapes. You can see the sky. You can see the brightest stars, but you cannot see the ground. You cannot see the branch in front of your face. You cannot see the edge of the cliff until you have already stepped over it. For billions of years, this was the fundamental divide of the nighttime world. Moonlit nights were navigable. Moonless nights were not. And evolution, with its relentless sensitivity to every variable that affects survival, built that divide into the fabric of terrestrial life. Consider the dung beetle. In 2013, a research team led by Marie Dake at Lund University in Sweden published a paper in Current Biology demonstrating that African dung beetles navigate at night by the light of the Milky Way. But they do not do this on moonlit nights. On moonlit nights, they navigate by the moon itself, rolling their balls of dung in straight lines calibrated to the position of the brightest object in the sky. The Milky Way navigation is a backup system, a fallback for the darkest nights when the moon is below the horizon or in its new phase. Remove the moon permanently, and you force every moonlight navigating species on the planet to rely exclusively on starlight, a signal more than 100 times fainter and far harder to calibrate against. The dung beetle is a small example. The large examples are more consequential. Across the savannas of Africa, the relationship between moonlight and predation has been studied in detail. A landmark study published in PLOS One by Palmer and colleagues in 2017 analyzed lion kill data from Kruger National Park and found that lions are significantly more successful at hunting during the darkest nights, the period around the new moon, than during the full moon. The reason is straightforward. Lions are ambush predators. Their prey, zebra, wildebeest, buffalo, rely heavily on vision to detect approaching threats. On moonlit nights, prey animals can see well enough to maintain vigilance. On dark nights, they cannot. Kill rates spike during the new moon and crater during the full moon. The lunar cycle is, in effect, a monthly oscillation in the balance of power between predator and prey across an entire continent. This is not unique to Africa. Studies of coral reef fish have shown that many species adjust their nighttime behavior based on the lunar phase, feeding in open water during the full moon when they can see approaching predators and retreating to shelter during the new moon when they cannot. Nightjars, nocturnal insectivorous birds found across Europe, Asia, and Africa, have been shown to concentrate their foraging activity around the full moon when they can see flying insects silhouetted against the moonlit sky. Owls, which hunt primarily by sound, actually experience reduced hunting success during the full moon because their rodent prey becomes more cautious in the increased light. The entire predator-prey dynamic of the nighttime world oscillates with the lunar cycle and has been doing so for hundreds of millions of years. Remove the moon, and every night becomes a new moon night. The darkest possible configuration of the sky becomes the permanent state. Prey animals lose their monthly respite from predation pressure. Visual hunters lose their monthly advantage. The equilibrium that has governed nocturnal ecosystems for longer than any species currently alive has existed, an equilibrium calibrated to the 29.5-day cycle of lunar phases, would be destroyed. Not by any change in the animals themselves, but by the removal of the light source around which their behavior evolved. The downstream effects would cascade. Species that rely on moonlight for navigation during migration, and there are many, would be affected. The monarch butterfly, for instance, uses a combination of the sun's position and the Earth's magnetic field for its primary navigation during its 3,000-mile migration from Canada to Mexico. But the moon may play a supplementary role in orientation during nighttime flight segments. The evidence is less conclusive here than for other species, but what is clear is that moonlight governs the timing of many migratory departures. Multiple studies have shown that migratory songbirds in Europe and North America preferentially depart on clear nights around the full moon, when they can see landmarks and maintain visual orientation during the critical first hours of flight. Remove the moon, and you darken every departure night equally. Sea turtles provide perhaps the most poignant example. Hatchling sea turtles, emerging from their nests on beaches around the world, orient toward the brightest horizon, which, under natural conditions, is always the ocean. The ocean horizon is brighter because it reflects starlight and moonlight from the open sky, while the landward horizon is darker due to the silhouettes of dunes and vegetation. This brightness differential is the hatchling's primary survival mechanism. They scramble toward the light, reach the water, and begin their long journey into the open sea. In the modern world, this instinct has already been disrupted by artificial lighting along coastlines, which draws hatchlings toward roads and buildings instead of the ocean. But even in areas where light pollution has been controlled, the hatchlings depend on the natural brightness differential, created in part by moonlight reflecting off the ocean surface. On moonless nights, the differential is reduced, and hatchling disorientation rates increase. A permanently moonless world would not eliminate the brightness differential entirely. Starlight would still create some contrast, but it would diminish it, adding yet another stressor to species already facing threats from warming oceans, plastic pollution, and habitat loss. But the ecological consequences of permanent darkness, as significant as they are, operate on biological timescales, decades to centuries for populations to adjust or collapse. The moon's disappearance would trigger a much more fundamental physical change in the Earth system, one that operates on geological timescales, but whose beginnings would be measurable within a human lifetime. The Earth would begin to speed up. Recall the tidal mechanism described earlier. The moon's gravity raises tidal bulges in both the oceans and the solid body of the Earth. Those bulges, dragged forward by the Earth's faster rotation, exert a gravitational pull on the moon that transfers angular momentum from the Earth to the moon. This transfer slows the Earth's rotation and pushes the moon outward. Remove the moon, and you remove the primary brake on the Earth's spin. The sun also exerts tidal forces on the Earth, and solar tides would continue to slow the planet's rotation, even without the moon. But the sun's tidal braking effect is only about 46% as strong as the moon's. With the moon gone, the total tidal drag on the Earth's rotation would be cut by more than half. This does not mean the Earth would immediately begin spinning faster. Angular momentum is conserved. The Earth's current rotation rate, one revolution every 23 hours, 56 minutes, and 4 seconds, is the product of 4.5 billion years of cumulative tidal braking. Removing the moon does not give back the angular momentum that has already been transferred. The Earth would not suddenly revert to its ancient 5-hour day. What would change is the rate of future deceleration. Instead of losing 2.3 milliseconds per century, the Earth would lose approximately 1.1 milliseconds per century, the solar tidal breaking alone. The day would still be getting longer, but at half the current rate. Over human timescales, this difference is negligible. Over geological timescales, it is transformative. Consider what happens when you project the reduced breaking rate forward. Currently, in about 200 million years, the Earth's day will have lengthened to approximately 25 hours due to continued lunar tidal breaking. Without the Moon, that same 200 million year period would see the day lengthen to only about 24 hours and 30 minutes, a half-hour difference that might seem trivial until you consider the cumulative effect over billions of years. But the more consequential scenario is not what happens in the future. It is what would have happened in the past had the Moon never existed. Without 4.5 billion years of lunar tidal breaking, the Earth would still be spinning at something close to its primordial rate. A day would last not 24 hours, but perhaps 8 to 10 hours. And a world spinning that fast is a very different place from the one you know. The Coriolis effect, the apparent deflection of moving air and water caused by the Earth's rotation, scales directly with the rotation rate. A planet spinning 2 to 3 times faster than the current Earth would have a Coriolis effect 2 to 3 times stronger. This would fundamentally reshape the atmospheric circulation. On the current Earth, the atmosphere is organized into 3 major circulation cells in each hemisphere: the Hadley cell, the Ferrel cell, and the polar cell. These cells create the prevailing wind patterns, the jet streams, the trade winds, and the storm tracks that govern weather and climate. The width and structure of these cells are determined in part by the Coriolis effect. A stronger Coriolis effect compresses the cells, making them narrower and more numerous. On a rapidly spinning Earth, you would not have 3 cells per hemisphere. You might have 5 or 6. The jet streams would be stronger, the trade winds would be more intense, storms would be more compact, but potentially more violent. The atmospheric energy budget would be redistributed in ways that no current climate model can fully predict. Wind speeds would increase. On the current Earth, the strongest sustained surface winds during hurricanes reach approximately 190 miles per hour. On a rapidly spinning Earth, the theoretical maximum for tropical cyclone wind speeds increases substantially. Some models suggest sustained winds in excess of 300 miles per hour would be physically achievable. The storms would be smaller in diameter, but more intense, feeding off the enhanced Coriolis-driven vorticity of a faster spinning atmosphere. The oceans would change shape. The faster the Earth spins, the larger the equatorial bulge. Currently, the equatorial diameter exceeds the polar diameter by about 26 miles. This is the ablateness created by the current rotation rate. A planet spinning once every 8 hours would have a substantially larger equatorial bulge. Sea level at the equator would be higher relative to the poles, and the redistribution of ocean water would alter coastlines globally. The equatorial oceans would be deeper. The polar oceans would be shallower. The geography of the continental shelves, the shallow underwater margins where most marine life concentrates, would be fundamentally different. None of this would happen overnight if the Moon vanished now, because the Earth's current rotation rate is already the product of 4.5 billion years of breaking. The Moon's disappearance would not make the Earth spin faster. It would merely reduce the rate at which it continues to slow down. But this thought experiment reveals something profound about the Moon's historical role. The Moon has not just been steadying the Earth's axis, it has been steadying the Earth's atmosphere, its oceans, its winds, and its weather by slowly, patiently, over billions of years, bringing the planet's spin down from a chaotic 5-hour whirl to the gentle 24-hour rhythm that allows the climate systems we depend on to exist in their current form. Without that breaking, Earth would be a world of perpetual gales, compressed climate zones, violent storms, and rapid day-night cycles that would stress every biological system. Photosynthesis would operate in short, intense bursts. The temperature differential between the day and night sides of the planet would be smaller, less time for each side to heat or cool, but the wind speeds needed to redistribute that heat would be extreme. The surface of the Earth would be windswept, storm-battered, and inhospitable to the kind of slow, patient evolutionary processes that produced forests, grasslands, and the large, slow metabolizing animals, including humans, that depend on them. This is the second great gift of the moon, after axial stabilization. It gave us calm, not perfect calm. The Earth still has hurricanes, tornadoes, and blizzards, but calm relative to what the planet would experience without 4.5 billion years of tidal deceleration. The 24-hour day is not an accident of physics. It is the product of the moon's patient, gravitational hand on the planet's shoulder, slowing it down year after year, century after century, epoch after epoch, until the spin rate reached the gentle pace that allows complex life to thrive. And there is still more, because the moon's disappearance would have consequences that extend beyond the surface of the Earth, beyond the atmosphere, beyond even the biosphere. It would reach into the deep interior of the planet itself, into the churning ocean of liquid iron that generates the magnetic field, the invisible shield that is, in many ways, the most important boundary between the Earth and the lethal environment of space. The Earth's magnetic field is generated by the geodynamo, a self-sustaining process in which convective currents of electrically conducting liquid iron in the outer core, combined with the Coriolis effect from the Earth's rotation, generate a dipolar magnetic field that extends tens of thousands of miles into space. This field deflects the solar wind, a continuous stream of charged particles blasting outward from the sun at speeds of 250 to 500 miles per second. Without the magnetic field, the solar wind would interact directly with the Earth's upper atmosphere, gradually stripping away lighter molecules, particularly hydrogen and oxygen, through a process called sputtering. This is not speculation, it is observation. Mars once had a magnetic field. When its core cooled and the dynamo shut down approximately 4 billion years ago, the solar wind began eroding the Martian atmosphere. NASA's MAVEN mission, Mars Atmosphere and Volatile Evolution, has been measuring this process since 2014, and the results are striking. Mars is currently losing about 100 grams of atmosphere per second to the solar wind. Over 4 billion years, this process has stripped Mars of most of its original atmosphere, reducing the surface pressure to 0.6% of Earth's. The water that once flowed on the Martian surface evaporated into the thinning atmosphere and was lost to space. Mars went from a potentially habitable world to a cold, dry desert, and the loss of its magnetic field was a primary cause. The Earth's magnetic field has protected it from this fate. But the geodynamo is not invincible. It requires 3 things to function: an electrically conducting fluid, convective motion in that fluid, and rotation. The Earth has all 3. The outer core is liquid iron. Convection is driven by the cooling of the core and by the crystallization of the solid inner core, which releases latent heat and light elements that drive buoyancy currents. And the rotation, the Coriolis effect, organizes those convective currents into the helical patterns that generate a coherent magnetic field. What role does the moon play in this process? The answer is debated among geophysicists, but a provocative hypothesis published by Denise Andreau and colleagues in 2016 in the journal Earth and Planetary Science Letters argues that tidal heating from the moon may contribute a significant fraction of the energy budget of the Earth's core. The idea is that the same tidal forces that deform the oceans and the solid Earth also deform the liquid outer core. This continuous tidal flexing dissipates energy as heat within the core, supplementing the radiogenic and gravitational energy that drives convection. If this hypothesis is correct, and it remains an active area of research, then the moon's disappearance would reduce the energy available to drive the geodynamo. The core would not cool immediately. The thermal inertia of the Earth's interior is enormous. It takes billions of years for significant heat loss to occur. But the reduction in tidal heating could, over geological timescales, weaken the convective vigor of the outer core. A weaker convection would mean a weaker magnetic field. A weaker magnetic field would mean less protection from the solar wind. And less protection from the solar wind, sustained over billions of years, would mean a gradual, irreversible loss of atmosphere. This is the most speculative of the moon's contributions, and it is important to be honest about the uncertainty. The Andro hypothesis has not been confirmed. Other researchers have argued that tidal heating in the core is negligible compared to radiogenic heating and inner core crystallization. The geodynamo would almost certainly continue to operate without the moon. The Earth's rotation and core convection would still produce a magnetic field. But the possibility that the moon contributes to the energy budget that sustains the geodynamo, that its gravitational influence reaches all the way down to the boundary between the outer core and the mantle, 1,800 miles below the surface, is a stunning illustration of how deeply this object is woven into the Earth system. Even if the moon's contribution to the geodynamo is minimal, its removal would still affect the magnetic field indirectly. The geodynamo depends on the Coriolis effect, which depends on the Earth's rotation rate. As we have established, the moon has been decelerating the Earth's rotation for 4.5 billion years. Counterintuitively, this deceleration may have actually helped the geodynamo by keeping the rotation rate in a range that produces a strong, stable, dipolar field. Some models suggest that very rapidly rotating planets may generate more complex, multipolar magnetic fields with many poles rather than two, which are less effective at deflecting the solar wind. By slowing the Earth to a moderate rotation rate, the moon may have helped ensure that the geodynamo produces the simple, strong, dipolar field that is most effective at protecting the atmosphere. This is layers upon layers. The moon slowed the Earth's spin, which helped produce a stable magnetic field, which protected the atmosphere from solar wind erosion, which preserved the oceans and the volatile molecules that life depends on. Remove any link in that chain, and the entire system is compromised. Not immediately, not dramatically, but incrementally, inexorably, over the deep time that is the natural currency of planetary evolution. We are now deep into the cascade of consequences, and a pattern is emerging. The moon's disappearance would not produce a single catastrophe. It would not trigger an extinction event next Tuesday. It would initiate a slow, compounding degradation of the conditions that make this planet habitable. Tidal rhythms disrupted, ecosystems destabilized, axial tilt drifting toward chaos, atmospheric protection potentially weakened, each consequence amplifying the others, each operating on a different time scale, some immediate, some spanning millennia, some requiring millions of years to manifest, but all pointing in the same direction, toward a planet that is less stable, less predictable, less hospitable to the kind of complex, interconnected biosphere that currently exists. And yet we have not yet reached the deepest layer of the moon's influence on Earth, because the most profound question is not what the moon does for us now. It is what the moon did for us at the very beginning. The question is not what would happen if the moon disappeared tonight. The question is whether life, complex, multicellular, intelligent life could have arisen on this planet at all without the moon's influence over the last 4.5 billion years? And the answer to that question takes us back to the very beginning, to the cooling of the magma ocean, to the formation of the first seas, to the tidal pools where chemistry first crossed the threshold into biology, to the long, patient, almost inconceivably slow process by which a barren rock became a living world. The moon was there for all of it, and it may have made all of it possible. The question of how life began on Earth remains one of the deepest unsolved problems in all of science. We know that by approximately 3.8 billion years ago, less than 700 million years after the planet formed, something on Earth had crossed the threshold from complex chemistry to self-replicating biology. We know this because of isotopic signatures in ancient rocks from Iswa, Greenland, and possibly from even older zircon crystals from Jack Hills, Western Australia, that suggest biological carbon fractionation as early as 4.1 billion years ago. Life appeared on Earth almost as soon as conditions permitted it. The transition from non-life to life happened either extraordinarily quickly or began even while the planet was still cooling from the aftermath of the Theia impact. But where did it happen? In what environment did simple molecules assemble into the first self-replicating systems? There are several competing hypotheses. Deep-sea hydrothermal vents, volcanic hot springs, ice-covered oceans, even meteorite impact craters. But one of the oldest and most persistent ideas places the origin of life in a setting that could not have existed without the moon. Tidal pools. The tidal pool hypothesis, in its modern form, draws on the observation that the origin of life requires not just the right chemistry, but the right dynamics. Specifically, it requires cycles of wetting and drying. The reason is that many of the key molecular assembly processes believed to have preceded life, the formation of long-chain polymers from simple monomers, the concentration of dilute organic molecules into reactive pools, the assembly of lipid membranes, are dramatically enhanced by repeated cycles of hydration and dehydration. Consider the problem of polymerization. The building blocks of life, amino acids, nucleotides, are small molecules dissolved in water. To form the large molecular chains that constitute proteins and nucleic acids, these monomers must be joined together by condensation reactions. Reactions that release a water molecule for each bond formed. But condensation reactions are thermodynamically unfavorable in water. You are trying to remove water from a system that is saturated with water. It is like trying to dry a sponge by dipping it in the ocean. The equilibrium favors breakdown, not assembly. The solution, first proposed by John Desmond Bernal in the 1940s and refined by subsequent researchers, is to periodically remove the water. If a dilute solution of organic monomers is allowed to dry, concentrating the monomers on a surface and removing the water that inhibits condensation, the monomers can link together into short polymers. If the surface is then re-wetted, the polymers dissolve, interact, and recombine. If the cycle repeats, wet, dry, the polymers grow longer and more complex with each iteration. This is exactly what happens in a tidal pool. Twice a day, roughly every 12 hours and 25 minutes, the tide comes in and goes out. A small depression in the rock along the shoreline is flooded with seawater, then exposed to air and sunlight as the water drains away. The organic molecules dissolved in the water are concentrated as the pool evaporates. Chemical reactions proceed on the exposed mineral surfaces. Then the tide returns, re-wetting the surface, dissolving the products, mixing them with fresh reactants from the sea, and starting the cycle again. The tidal pool is not just a puddle, it is a natural chemical reactor, cycling between wet and dry states with a regularity governed by the moon's orbit. In the early Earth, when the moon was much closer and the tidal ranges were vastly larger than today, would have had tidal pools of extraordinary scale and energy. When the moon was 15,000 miles away, tidal ranges in some coastal configurations may have been hundreds of feet. The intertidal zone would have been not a narrow strip, but a vast, constantly shifting landscape of pools, channels, flats, and basins, all cycling between flooded and exposed states at a pace far faster than today's leisurely, twice-daily rhythm. The early moon was so close that tides would have cycled much more rapidly, with the period dependent on the Earth's faster rotation and the moon's closer orbit. Could life have originated in these primordial tidal flats? The hypothesis is unprovable with current evidence. We cannot go back 4 billion years and watch chemistry become biology, but the circumstantial case is strong. The tidal pool provides every condition that origin of life researchers have identified as important. Wet-dry cycling for polymerization, mineral surfaces for catalysis, concentration of dilute reactants through evaporation, UV radiation from the young sun for energy input, and periodic refreshment of reactants from the open ocean. No other known environment on the early Earth provides all of these conditions simultaneously with the kind of regular, predictable cycling that the tides deliver. And the tides on the early Earth were overwhelmingly the moon's creation. Solar tides existed then as they do now, but the moon's contribution, with its extreme proximity and the resulting extreme tidal forces, would have dwarfed the solar component. The tidal environment of the early Earth was the moon's gift. If the moon had never formed, if Theia had missed, or had struck at a different angle, or had been absorbed entirely without ejecting debris, the early Earth would have had only solar tides. Those tides would have been approximately 1/3 the height of even today's lunar-dominated tides, and they would have lacked the twice-daily rhythm that the moon's orbital period creates. The intertidal zone would have been a thin, sluggish strip rather than a vast, dynamic landscape. The wet-dry cycling that may have driven prebiotic chemistry would have been weaker, slower, and less extensive. Would life still have arisen? Perhaps. The hydrothermal vent hypothesis does not require the moon. The volcanic hot springs model does not require the moon. It is possible, even likely, that some form of microbial life would have eventually emerged on a moonless Earth, given enough time and enough chemistry. But the tidal pool hypothesis offers something the other models do not: a mechanism for rapidly, repeatedly, and reliably cycling the chemical conditions necessary for molecular complexity to increase. If this mechanism was important, if it was the difference between life arising in 100 million years versus 500 million years, or the difference between life arising at all versus remaining stuck at the threshold of prebiotic chemistry, then the moon's role in the origin of life is not peripheral, it is foundational. There is another dimension to the moon's influence on early Earth that is less speculative and more directly supported by physics. The giant impact that created the moon also transformed the Earth in ways that were essential for the planet's subsequent evolution. Before the Theia impact, the proto-Earth was a partially differentiated body. Its iron core was forming, but the mantle was not yet fully stratified. The catastrophic energy of the impact, those 10 to the 32nd joules, remelted the entire planet, creating a global magma ocean that extended to a depth of at least 1,000 miles and possibly much deeper. This wholesale melting allowed the Earth's interior to fully differentiate. Dense iron sank efficiently to the center, forming the large, dense core that drives the geodynamo. Lighter silicates floated to the surface, forming the mantle and the proto-crust. Volatile elements, water, carbon dioxide, nitrogen, were degassed from the magma into the early atmosphere. Without the Theia impact, Earth's differentiation would have been less complete. The core might have been smaller. The mantle might have been more heterogeneous. The geodynamo might have been weaker or might have taken longer to establish. The degassing that produced the early atmosphere and ultimately the oceans might have been less efficient. In a very real sense, the impact that created the moon also created the Earth as we know it. A planet with a large iron core, a strong magnetic field, a well-mixed mantle capable of sustaining plate tectonics, and a volatile rich surface capable of hosting oceans. Plate tectonics deserves special attention here because its relationship to the moon is more subtle and more debated than any of the other connections we have explored. Plate tectonics, the slow movement of rigid lithospheric plates across the Earth's surface, driven by convection in the underlying mantle, is arguably the single most important geological process for maintaining long-term habitability. It recycles carbon between the atmosphere and the interior through the carbonate-silicate cycle, acting as a planetary thermostat that prevents runaway greenhouse warming or runaway glaciation. It creates mountain ranges that drive weather patterns and create biodiversity hotspots. It maintains ocean chemistry by cycling elements through subduction zones and mid-ocean ridges. It is, in a sense, the circulatory system of the planet. Does the moon drive plate tectonics? No. The primary energy source for plate tectonics is internal heat, radiogenic heating from the decay of uranium, thorium, and potassium in the mantle, supplemented by secular cooling and the latent heat released by the crystallization of the inner core. The moon's tidal forces do not have enough energy to move tectonic plates. However, the Theia impact may have created the conditions that made plate tectonics possible. Several researchers have argued that Earth's plate tectonics, unique among the terrestrial planets in our solar system, requires a specific set of initial conditions: a mantle with the right viscosity and composition, a crust thin enough to fracture into plates, enough internal heat to drive convection, and enough water in the mantle to weaken the rock and enable subduction. Venus, which is similar to Earth in size and composition but lacks plate tectonics, may differ precisely because it lacks one or more of these conditions, possibly because it never experienced a giant impact equivalent to the Theia event. The giant impact hypothesis suggests that the Theia collision provided several of these conditions. The remelting and redifferentiation of the mantle established the compositional and thermal profile necessary for vigorous convection. The stripping away of a portion of the protocrust, as ejecta, that formed the moon may have left the remaining crust thinner and more prone to fracturing into plates. And the enormous thermal pulse from the impact set the initial condition for the billions of years of mantle convection that followed. This is speculative. The relationship between the moon-forming impact and the initiation of plate tectonics is not established to the same degree of confidence as, say, the moon's role in axial stabilization. But the possibility is there, and it is worth sitting with. If the moon-forming impact was necessary for plate tectonics, even if it was only one of several necessary conditions, then the chain of consequences becomes almost absurdly long. The impact created the moon, which stabilized the axis, which stabilized the climate. The impact created the tidal forces that may have driven prebiotic chemistry. The impact melted the Earth, which enabled complete differentiation, which created the geodynamo, which generated the magnetic field, which protected the atmosphere. And the impact may have set the initial conditions for plate tectonics, which maintained the carbon cycle, which regulated the climate, which kept the oceans liquid, which allowed life to persist and diversify over billions of years. Every link in this chain leads back to the same event. One collision, one impact, one object, Theia, striking the proto-Earth at the right angle at the right speed, at the right time, and in the process creating not just the moon but the Earth as a habitable world. Let us now return to the thought experiment. The moon has vanished. The immediate consequences, tidal disruption, darkness, ecological stress, have played out over weeks and months. The medium-term consequences, the beginning of axial drift, the absence of tidal breaking, are measurable within centuries. But the deep-time consequences, the ones that would play out over millions and billions of years, are the ones that reveal the moon's true significance. We have already discussed the chaotic axial oscillation that would begin within tens of millions of years. But there is another deep-time consequence that deserves attention, and it concerns not the Earth's orientation, but its orbital dynamics. The moon is not a small object. At 1.2% of Earth's mass, it is the largest satellite relative to its parent body in the inner solar system. The Earth-Moon system is often described not as a planet with a moon, but as a double planet. Two bodies orbiting a common center of mass, or barycenter, that lies about 1,000 miles beneath the Earth's surface. This barycenter orbits the Sun in a smooth ellipse, but the Earth and Moon each wobble around it in their mutual orbit. The Earth's center is not on the barycentric path. It oscillates around it with a displacement of about 2,900 miles over the course of each lunar month. Remove the Moon, and the Earth's center of mass shifts to the planet's geometric center. The monthly wobble vanishes. The Earth's orbit around the Sun becomes smoother, but also loses a subtle source of dynamical averaging that may have contributed to orbital stability over geological time. The effects of this change on Earth's long-term orbital dynamics are small but non-zero, and they interact with the gravitational perturbations from Jupiter and Venus in ways that are difficult to model over billion-year timescales. More significantly, the Moon's gravitational influence helps determine the precession rate of the Earth's orbit, the slow rotation of the orbital ellipse itself, which affects the timing and intensity of climate cycles. The Milankovitch cycles, the periodic variations in Earth's orbit that drive ice ages, are governed by three parameters: eccentricity, the shape of the orbit, with a period of about 100,000 years; obliquity, the axial tilt, with a period of about 41,000 years; and precession, the wobble of the axis and the rotation of the orbit, with a combined period of about 21,000 years. The obliquity cycle is directly controlled by the Moon, as we have discussed. The precession cycle is also influenced by the Moon, because the rate of axial precession depends on the torques exerted on the equatorial bulge, torques that come from both the Sun and the Moon. Remove the Moon, and the Milankovitch cycles change. The obliquity cycle ceases to be a gentle 2.4-degree oscillation and becomes the chaotic wandering described by Laskar. The precession cycle changes its period and amplitude. The eccentricity cycle, driven primarily by Jupiter's gravitational influence, would be less affected but would interact differently with the altered obliquity and precession cycles. The entire rhythm of Earth's climate variability, the rhythm that has driven ice ages and interglacials for the last 2.5 million years, would be disrupted and replaced by something more chaotic, less predictable, and potentially more extreme. Ice ages may seem like disasters, but they are actually essential to the long-term habitability of the Earth. The Milankovitch-driven oscillation between glacial and interglacial periods has been one of the most powerful drivers of evolution in the last few million years. It created the climate variability that drove human ancestors from forests to savannas, that selected for intelligence, adaptability, and tool use, that forced populations to migrate, split, reconnect, and innovate. The ice ages did not just happen to us, they shaped us. And the rhythm of the ice ages was set, in large part, by the Moon. This is the deepest irony of the thought experiment. The Moon did not merely create the conditions for complex life, It created the conditions for the specific kind of complex life that would eventually look up at the moon and wonder what it was. The tidal pools that may have catalyzed the origin of life, the stable axis that allowed ecosystems to persist long enough for complexity to evolve, the moderate rotation rate that allowed calm enough weather for forests and grasslands, the magnetic field that kept the atmosphere intact, the Milankovitch cycles that drove the evolutionary pressures producing human intelligence. All of it traces back through chains of causation long and short, direct and indirect, to the presence of a dead, airless, 2,160-mile rock orbiting 238,900 miles away. The moon did not just witness the story of life on Earth, it wrote the opening chapters. It set the conditions for every chapter that followed, and it continues to turn the pages, even now, even tonight, with every tide that rises and every degree of axial tilt that holds steady against the gravitational pulling of Jupiter and the Sun. Remove it, and you do not merely darken the sky. You remove the author. But we are not yet finished with the cascade of consequences, because there is one more dimension of the moon's disappearance that is often overlooked in scientific analyses. It is not a physical consequence. It is not measurable with instruments or predictable with equations, but it may be, in its own way, the most immediate and the most deeply felt of all the losses. The cultural erasure. Every human civilization that has ever existed has built part of its identity around the moon. This is not a metaphor. It is an anthropological fact so pervasive that its absence would be almost inconceivable. The Islamic calendar is a purely lunar calendar. Its 12 months follow the synodic period of the moon, the 29.5-day cycle from new moon to new moon. And the beginning of each month is traditionally determined by the sighting of the crescent moon. The month of Ramadan, the holiest month in Islam, begins and ends with the observation of the crescent. The Hajj pilgrimage is timed by the lunar calendar. The entire liturgical rhythm of a religion practiced by nearly 2 billion people is synchronized to the moon. The Jewish calendar is lunisolar. Months follow the lunar cycle, with periodic intercalary, months added to keep the calendar roughly aligned with the solar year. The major holidays, Passover, Rosh Hashanah, Sukkot, Purim, are all dated by the lunar calendar. The Sabbath itself, while weekly, exists within a calendrical system built on the moon's phases. The Chinese calendar, the Hindu calendar, the Buddhist calendar, the traditional calendars of Japan, Korea, Vietnam, and many other cultures all incorporate the lunar cycle as a foundational timekeeping element. The Mid-Autumn Festival, Diwali, Vesak, Chuseok, each tied to the moon's phase, each an expression of the human instinct to organize life around the most visible cycle in the sky after the day itself. Beyond the calendar, the moon has shaped language. Monday, Moon Day in English, Lundi in French from Luna. The word month itself derives from moon in virtually every Germanic language. The word menstrual comes from the Latin mensis, meaning month, which itself derives from the Proto-Indo-European root for moon. Whether or not the human menstrual cycle is genuinely synchronized with the lunar cycle, the evidence is debated. The linguistic and cultural connection is ancient and deep. The moon has shaped navigation. For thousands of years before the invention of the magnetic compass, mariners navigated by the moon's position, using its known orbital period and phase to determine longitude on the open ocean. The lunar distance method, a technique for determining longitude by measuring the angular distance between the moon and a known star, was the primary method of celestial navigation from the 18th century until the advent of marine chronometers. The moon was not just a light in the sky. It was a clock, a compass, and a map. The moon has shaped art. From the earliest cave paintings to Van Gogh's Starry Night to the photographs of Ansel Adams, the moon has been one of the most depicted objects in human visual culture. It has shaped music. Beethoven's Moonlight Sonata, Debussy's Clair de Lune, countless folk songs and lullabies across every culture. It has shaped literature, from the lunar voyage of Lucian of Samosata in the 2nd century to Jules Verne to H.G. Wells to Arthur C. Clarke. It has shaped mythology so thoroughly that nearly every culture on Earth has a moon deity. Selene, Luna, Artemis, Diana, Chang'e, Tsukuyomi, Mani, Khonsu, Ixchel, Mamaquila. Remove the moon, and you do not merely alter the physical conditions of the planet. You erase an organizing principle of human civilization. You remove the timekeeper that governed planting and harvesting for 10,000 years of agriculture. You remove the beacon that guided every ocean crossing before the age of electronics. You remove the muse that inspired some of the greatest works of human creativity. You remove the deity that occupied a central place in the spiritual lives of billions of people across thousands of years. You remove the nightlight that every child has ever stared at through a bedroom window, wondering what it was and why it glowed and whether anyone was looking back. The moon is not scenery. It is infrastructure. Physical, biological, cultural, spiritual. It is woven into the fabric of what this planet is and what the creatures living on it have become. Its disappearance would not be an event. It would be an unraveling. We do not have to imagine what a terrestrial planet looks like without a large, stabilizing moon. We have an example. It is the 4th planet from the Sun, and its story is a cautionary tale written in rust and silence. Mars has 2 moons, Phobos and Deimos, but they are not moons in any meaningful dynamical sense. They are captured asteroids, tiny and irregular, orbiting close and fast. Phobos is 14 miles across at its widest. Deimos is 8 miles. Combined, they contain less than 1/10,000,000th of the mass of Earth's moon. They exert no significant tidal force on Mars. They do not stabilize the Martian axis. They do not break the Martian rotation. They are decorative, gravitationally irrelevant, a pair of cosmic pebbles circling a planet that, in every dynamical sense that matters, is alone. And Mars shows what that aloneness means. The current axial tilt of Mars is 25.19 degrees, coincidentally close to Earth's 23.44 degrees. This similarity is misleading. Earth's tilt is stable, held in place by the moon's gravitational influence. Mars's tilt is not stable. It is a snapshot of a value that has been wandering chaotically for billions of years. In 1993, the same year Lascar published his landmark paper on Earth's obliquity, he and his colleague Philippe Robutel also modeled the obliquity history of Mars. Their results were dramatic. Over the last 5 million years alone, Mars's axial tilt has swung between approximately 15 degrees and 35 degrees. Over longer timescales, tens of millions to hundreds of millions of years, the tilt has almost certainly reached values of 60 degrees or higher. Some models suggest excursions to 82 degrees. At 60 degrees of axial tilt, the Martian poles would point nearly at the sun during summer solstice. The polar ice caps, currently composed of frozen carbon dioxide and water ice, would sublime rapidly under direct solar illumination. The carbon dioxide released into the atmosphere would temporarily thicken it, potentially raising surface pressures and temperatures enough to allow liquid water to flow in the warmest regions. Then, as the tilt swung back toward lower values, the poles would refreeze, the atmosphere would thin, and the planet would return to its current cold, dry state. This is not speculation. It has left visible evidence on the Martian surface. The layered deposits at Mars's poles, thousands of feet of alternating light and dark bands visible in images from NASA's Mars Reconnaissance Orbiter, are believed to record these obliquity-driven climate cycles. Each layer represents a different climate regime, a different tilt, a different balance between ice and atmosphere. The Martian poles are a geological record of axial chaos, written in ice and dust over hundreds of millions of years. Mars also shows the consequences of lacking tidal braking. Without a significant moon to slow its rotation, Mars spins at approximately the same rate as Earth, one rotation every 24 hours and 37 minutes. But this similarity is coincidental. Mars has not been braked. Its current rotation period is close to its primordial value, modified only slightly by the weak tidal influence of the Sun and the negligible influence of Phobos and Deimos. If Mars had formed with a large moon, its rotation would have been slowed over billions of years, just as Earth's was. The similarity in day length between Earth and Mars is a cosmic accident, not a shared dynamical history. The most consequential difference, however, is the magnetic field. Mars once had one. Analysis of crustal magnetization patterns by NASA's Mars Global Surveyor, which orbited Mars from 1997 to 2006, revealed strong, banded magnetic anomalies in the ancient southern highlands, remnants of a global magnetic field that operated during the first billion years of the planet's history. The Martian dynamo shut down approximately 4 billion years ago, probably as the planet's smaller core cooled and convection ceased. Without its dynamo, Mars was defenseless against the solar wind. MAVEN has measured the ongoing atmospheric loss in real time, about 100 grams per second today, and almost certainly much more during the Sun's more active youth. Over 4 billion years, this erosion has reduced the Martian atmosphere from something thick enough to support liquid water to the wisp of carbon dioxide that exists today, a surface pressure of about 600 pascals, less than 1% of Earth's. Mars is what happens when a terrestrial planet lacks the stabilizing, protecting, braking influence of a large moon. Its axis wanders, its climate oscillates wildly, its atmosphere erodes, its water is lost to space. Whatever conditions might have once existed for life, and there is growing evidence that early Mars was warm and wet, were not sustained long enough for complexity to develop. Mars is not dead because it is small or because it is far from the Sun. It is dead because it is alone. It had no Theia. It had no giant impact. It had no moon. The comparison between Earth and Mars is the most powerful argument for the moon's importance, precisely because the two planets started with similar raw materials. Both formed in the inner solar system from the same protoplanetary disk. Both are rocky, differentiated bodies with iron cores. Both sit within the Sun's habitable zone, Mars at the outer edge, but still within it. The critical divergence in their histories was not distance or size, but a single catastrophic event that happened to one and not the other. Earth was struck by Theia. Mars was not. And 4.5 billion years later, one planet is teeming with life and the other is a frozen desert. This observation has led some planetary scientists to propose what might be called the rare moon hypothesis, an extension of the rare Earth hypothesis advanced by Peter Ward and Donald Brownlee in their 2000 book of the same name. Ward and Brownlee argued that while simple microbial life may be common in the universe, the specific conditions required for complex, multicellular life are so numerous and so improbable that Earth may be extraordinarily unusual among habitable worlds. The rare moon hypothesis goes further. It suggests that one of the most critical of those conditions, one that is often overlooked in discussions of habitability, is the presence of a large, stabilizing natural satellite. The argument is as follows. For a terrestrial planet to develop and sustain complex life over billions of years, it needs, at minimum, a stable axial tilt for climate predictability, a moderate rotation rate for manageable weather systems, a strong magnetic field for atmospheric retention, robust tidal forces for potential prebiotic chemistry, and plate tectonics for long-term carbon cycling and chemical renewal. The Moon contributes to all 5 of these requirements, directly or indirectly. How common are large moons around terrestrial planets? In our solar system, the answer is extraordinarily rare. Earth is the only terrestrial planet with a large, natural satellite. Venus has none. Mercury has none. Mars has only captured asteroids. The gas giants have large moons, Jupiter's Galilean satellites, Saturn's Titan. But these are ice rock bodies orbiting gas giants, not rocky companions to rocky worlds. The Earth-Moon system is unique in the inner solar system. Could large moons be common around terrestrial exoplanets? This is one of the most tantalizing open questions in exoplanetary science. As of now, no confirmed exomoon has ever been detected, despite extensive searches. The most promising candidate, Kepler 1625b, announced in 2018 by David Kipping and Alex Tichy at Columbia University, remains controversial, with subsequent analyses both supporting and questioning the detection. The difficulty is that exomoons are small, their transit signals are tiny, and they are buried in the noise of stellar variability. We simply do not yet have the technology to determine whether large moons around terrestrial exoplanets are common or vanishingly rare. But the physics of moon formation suggests they may be rare. The leading model for the formation of Earth's moon, the giant impact hypothesis, requires a very specific set of circumstances. The impactor must be roughly Mars-sized. The impact must occur at an oblique angle. The velocity must be high enough to eject material into orbit, but not so high that the material escapes the Earth's gravity entirely. The impact must happen early enough in the planet's history that the debris can coalesce efficiently, but late enough that the planet is already substantially formed. Change any of these parameters significantly, and you get a different outcome. Total accretion of the impactor with no moon, a ring system that fails to coalesce, a moon that is too small to stabilize the axis, or a catastrophic disruption that destroys the planet entirely. The giant impact is not a gentle process with broad tolerances. It is a low probability event that produces a high consequence outcome. And if the rare moon hypothesis is correct, if large stabilizing moons are indeed uncommon around terrestrial planets, then the disappearance of our moon would not merely transform the Earth. It would demote it. It would remove the characteristic that made this planet exceptional among the trillions of rocky worlds in the galaxy. It would turn Earth into the rule rather than the exception. Another Venus, another Mars, another rocky world with the raw materials for life, but not the conditions to sustain it. Let us now gather the threads. Let us lay out, in sequence, the full cascade of consequences that would follow the moon's disappearance from the first second to the deep future. Not to frighten, but to illuminate, to make visible the invisible architecture that the moon has built around this planet over 4.5 billion years. In the first second, every gravimeter and tidal monitoring station on Earth would register the disappearance. The solid Earth tide, the 30-centimeter breathing of the planet's crust, would begin to relax. Seismometers would record the signal. The gravitational environment of the Earth would shift instantaneously, though human beings would feel nothing. In the first hours, the tidal bulges in the oceans would begin to redistribute. The dominant lunar tidal component would cease. Complex wave interactions would propagate through every ocean basin as the water sought a new equilibrium under solar, only tidal forcing. the tidal range would begin to diminish toward approximately one-third its former value. In the first night, the sky would be dark. Not just new moon dark, which happens once a month and is familiar. Permanently dark. The nighttime illumination would drop from a maximum of 0.25 lux to a permanent 0.002 lux. Every nocturnal animal, every migrating bird, every spawning coral, every hatchling sea turtle would confront a world without its brightest, natural nighttime light source. Predator-prey dynamics would shift toward permanent, dark-adapted equilibria. In the first weeks, the new tidal regime would stabilize. Coastlines would begin to adjust. Intertidal zones would contract. Estuarine salinity patterns would shift. The biological communities of the world's shorelines would begin a slow, compounding decline as the habitat they evolved to occupy shrank by approximately 2/3. In the first years, the ecological consequences would compound. Coral spawning synchronization would begin to break down. Species dependent on lunar light cues for navigation, mating, or foraging would face increasing reproductive failure. Horseshoe crab spawning patterns would shift. Migratory chains linked to tidal and lunar cycles would fray. Mangrove forests and salt marshes, deprived of their full tidal flushing, would begin to degrade at their margins. In the first centuries, the rate of Earth's rotational deceleration would measurably decrease. The day would still be getting longer, but at approximately half the current rate. The difference would be detectable by atomic clocks within a few decades. Culturally, the absence of the moon would have reshaped calendars, religious observances, navigation methods, and the entire symbolic vocabulary of human civilization. A generation born after the moon's disappearance would know it only from history. In the first millennia, the Earth's axial tilt would begin to drift. Not dramatically. The timescale for chaotic obliquity oscillation is millions of years. But the precession rate would change, and the subtle gravitational perturbations from the Sun and Jupiter would begin to accumulate without the moon's stabilizing counterforce. Climate models would show the first faint signals of obliquity drift in their long-term projections. The Milankovitch cycles, as they had been understood for centuries, would begin to deviate from their established patterns. In the first millions of years, the axial tilt would enter the chaotic zone identified by Lascar. The obliquity would begin to oscillate with increasing amplitude, not smoothly, but erratically, driven by the complex gravitational interactions of the inner solar system. The tilt might remain near 23 degrees for millions of years, then swing to 40 degrees over a few million years, then swing further. The climate would follow. Ice sheets would advance and retreat at unpredictable intervals. Temperature zones would shift. Ecosystems that had persisted for millions of years would collapse as the seasonal patterns they depended on became unreliable. In the first tens of millions of years, the obliquity oscillations would reach extreme values. Tilts of 50, 60, 70 degrees would become possible. At these tilts, the poles would receive more annual solar energy than the equator during their respective summers. The climate would become unrecognizable. Ice sheets would form at the equator during periods of low tilt, then melt as the tilt swung high. The temperature gradient between equator and poles would reverse, then reverse again. The atmospheric circulation patterns would reorganize repeatedly. Each reorganization would be a mass extinction event for species unable to adapt quickly enough. In the first hundreds of millions of years, the compounding effects of axial chaos, altered wind patterns, disrupted ocean circulation, and potentially weakened magnetic field shielding would render the Earth progressively less hospitable to complex life. The specific trajectory would depend on variables we cannot predict. The timing and amplitude of the obliquity oscillations, the response of the ocean atmosphere system, the resilience of microbial life versus multicellular organisms. But the general direction is clear. Without the moon, the Earth would become more like Mars, not immediately, not in the same way, but in the same direction. More variable, more extreme, less able to sustain the stable conditions that complex ecosystems require. This is not an apocalypse, it is an erosion. The moon's disappearance would not end the world in fire or ice. It would slowly, inexorably remove the conditions that make this particular world, this temperate, moderate, seasonally predictable, tidally rhythmic, magnetically shielded, axially stable world, possible. What would remain would still be a planet. It would still orbit the sun. It might still host microbial life in deep rock aquifers or hydrothermal systems, clinging to existence in the cracks and margins of a deteriorating surface environment. But it would not be Earth as we know it. It would not be the planet that produced forests and oceans and coral reefs and birds and whales and human beings. It would be a planet that had lost its partner. And in the arithmetic of planetary habitability, the partner may have mattered more than anyone realized. But here, at the deepest point of this cascade, at the moment when the implications seem most bleak, there is a revelation waiting. Not a silver lining, not a comfort. Something more interesting than that. A recognition. The moon is dying. Not tonight. Not soon. But inevitably, on a time scale that is long by human standards and short by cosmic ones, the Earth-Moon system is approaching its own endpoint. And understanding that endpoint transforms this entire thought experiment from a catastrophe into a love story. Recall the fundamental mechanism. The moon is receding from the Earth at 3.8 centimeters per year, powered by the tidal transfer of angular momentum. As the moon moves outward, the tidal forces it exerts on the Earth weaken. Tidal force declines with the cube of the distance. As the tidal forces weaken, the rate of angular momentum transfer decreases. The moon's outward migration is decelerating. It is moving away more slowly now than it was 1 billion years ago, and it will move away more slowly in 1 billion years than it does now. Eventually, in approximately 50 billion years, according to some models, the Earth-Moon system would reach tidal lock. The Earth's rotation would slow until one day equaled 1 lunar month. The moon's outward migration would cease, because the tidal bulge would no longer be dragged ahead of the moon's position. It would point directly at the moon, in perfect alignment, exerting no net torque. The Earth and moon would face each other in permanent lockstep, the same face of each body always pointing toward the other. Just as the moon is already tidally locked to the Earth, which is why we always see the same face, the Earth would eventually become tidally locked to the moon. But there is a complication. 50 billion years is approximately 10 times the current age of the solar system, and it is roughly 5 times longer than the sun has before it exhausts its hydrogen fuel and expands into a red giant. In approximately 5 billion years, the sun will swell to a diameter large enough to engulf Mercury and Venus, and possibly the Earth. Even if the Earth survives the red giant phase, which is uncertain, the solar system in 50 billion years will be unrecognizable. The sun will have become a white dwarf. The inner solar system will have been transformed beyond recognition. The Earth-Moon tidal lock will never be achieved. The sun will die first. The system that has been patiently, elegantly transferring angular momentum from one body to another for 4.5 billion years will be interrupted before it reaches completion. The dance will end not because the dancers stopped, but because the music hall burned down. There is something melancholy in this, and something profound. The moon has been slowing the Earth, steadying the Earth, protecting the Earth, shaping the Earth for its entire existence, and it will continue to do so for as long as the sun shines. But the relationship has an expiration date that is not set by the moon or the Earth, but by the star they both orbit. The system is not eternal. It is a phase, a long, beautiful, extraordinarily productive phase, one that has lasted long enough to produce every living thing that has ever existed on this planet. But a phase nonetheless, and that perhaps is the deepest insight of this entire thought experiment. For most of the history of astronomy, the search for habitable worlds has focused on a single variable: distance from the star. The habitable zone, the orbital region where liquid water can exist on a planet's surface, has been the primary criterion for identifying worlds that might host life. Find a rocky planet in the habitable zone, and you have found a candidate. This is the framework that guided the Kepler mission, the TESS mission, and the early architecture of the James Webb Space Telescope's Exoplanet Observation Program. It is a useful framework. It is also radically incomplete. The story of the moon, the full story, from Thea's impact to the tidal stabilization of the axis, to the breaking of the rotation, to the potential catalysis of prebiotic chemistry, reveals that distance from the star is not enough. A planet can sit perfectly within the habitable zone, with the right mass, the right composition, the right atmosphere, and still fail to develop complex life because it lacks the dynamical conditions that only a large, natural satellite can provide. Axial stability, tidal rhythm, rotational moderation, magnetic field support. These are not secondary considerations. They are, potentially, as important as the distance from the star itself. This transforms the search for life in the universe. It means that when we examine an exoplanet in the habitable zone, when we analyze its atmosphere with JWST and look for biosignatures like oxygen, methane, and water vapor, we should also be asking, does it have a moon? And not just any moon, a large moon. A moon massive enough to stabilize the planet's axis against the gravitational perturbations of its star and neighboring planets. A moon formed by the kind of catastrophic impact that simultaneously reshapes the planet's interior, accelerates its differentiation, and creates the conditions for a strong, persistent magnetic dynamo. We do not yet have the technology to answer this question for most exoplanets. As mentioned earlier, no confirmed exomoon detection has been achieved despite extensive search programs. The transit timing variations and transit duration variations that would reveal a large exomoon are at the edge of current instrument sensitivity. But the question has been framed. The rare moon hypothesis has entered the vocabulary of astrobiology. And the moon, our moon, the one hanging in our sky tonight, is the reason why. This is what the thought experiment reveals. Not just that the moon matters, not just that its disappearance would be catastrophic, but that the moon is a lens through which we can see the full complexity of what makes a planet habitable. It is a reminder that habitability is not a single condition, not a temperature range, not a chemical formula, not a distance measurement, but a system. A network of interlocking physical processes, each depending on the others, each traceable to specific initial conditions, each capable of being disrupted by the removal of a single component. The moon is one of those components, and it may be the one that is hardest to replace. Consider the alternatives. If the moon vanished, could anything substitute for its functions? Could we, with advanced technology, stabilize the Earth's axis artificially? In principle, perhaps. The torques involved are enormous. The moon exerts a gravitational force on the Earth's equatorial bulge that would require energy inputs far beyond any technology we currently possess to replicate. but in principle, some form of massive orbital infrastructure, a swarm of dense bodies positioned to exert the right gravitational torques, might serve as a crude substitute. The engineering challenges would be beyond anything humanity has ever attempted. The energy requirements would be staggering, but physics does not forbid it. Could we replace the tides? Not meaningfully. The gravitational interaction between the moon and the Earth's oceans is a planetary scale phenomenon. No mechanical system could replicate the simultaneous, global, continuous redistribution of trillions of tons of seawater twice a day. The tidal ecosystem would be lost. Could we replace the moonlight? Trivially, in a sense. Artificial satellites with reflective surfaces could provide illumination, but the quality of light, its spectral composition, its directional characteristics, its monthly variation, would be different. The ecological systems calibrated to the specific luminance profile of the full moon would not respond to an artificial substitute in the same way. Could we replace the cultural presence? No. A civilization that grew up without the moon would be a different civilization. Its calendars, its myths, its art, its poetry, its religions, its languages, its metaphors, its dreams, all would be built on different foundations. The moon is not interchangeable. It is not a feature that can be patched or upgraded. It is a 4.5 billion year presence that has shaped the deepest structures of life and culture on this planet. And its absence would be an absence, a void in the sky and in the collective consciousness of every living thing that ever evolved under its light. Let us return one final time to the physics, because there is one more number that deserves attention. One more fact that more than any other captures the improbability and the significance of what orbits above us. The moon's diameter is 2,159 miles. The sun's diameter is 864,340 miles. The sun is therefore approximately 400 times wider than the moon. The sun is also approximately 400 times farther from the Earth than the moon. These two ratios, 400 to 1 in size, 400 to 1 in distance, cancel each other almost exactly. The result is that the moon and the sun appear almost precisely the same size in the Earth's sky. The angular diameter of the moon is approximately 0.52 degrees. The angular diameter of the sun is approximately 0.53 degrees. This is a coincidence. There is no physical law that requires it. There is no gravitational mechanism that produces it. It is a pure, improbable, transient accident of the current orbital configuration of the Earth-Moon-Sun system. Transient because the moon is receding. 400 million years ago, the moon was closer and appeared larger in the sky. In 600 million years, it will be farther and appear smaller. The period during which the moon and sun appear the same size in the sky is a window, a few 100 million years wide, and we happen to exist within it. The consequence of this coincidence is one of the most spectacular phenomena in all of nature: the total solar eclipse. When the moon passes between the Earth and the sun, and when the alignment is precise enough, the moon's disk covers the sun's disk almost perfectly. The blazing photosphere is hidden, and for a few minutes, never more than about 7 minutes and 32 seconds, usually much less, the sun's corona becomes visible. That ethereal, pearlescent halo of superheated plasma, normally invisible against the overwhelming brightness of the photosphere, is revealed in all its delicate, structured beauty. Total solar eclipses are, arguably, the most visually stunning natural phenomenon accessible to human observers. They are also scientifically invaluable. It was during a total solar eclipse in 1919 that Arthur Eddington measured the deflection of starlight by the sun's gravity, confirming Einstein's general theory of relativity. It was during eclipses that the element helium was first detected in the solar spectrum, discovered in the sun before it was found on Earth, and named for Helios, the Greek god of the sun. Eclipse observations have contributed to our understanding of solar physics, coronal dynamics, and the testing of fundamental physical theories. None of this would be possible without the coincidence of apparent sizes. If the moon were significantly smaller or significantly farther away, it would not fully cover the sun during transit. There would be annular eclipses, but no total eclipses. The corona would remain hidden. Eddington's test of general relativity would have had to wait for a different method. The discovery of helium might have been delayed. The entire aesthetic and scientific tradition of eclipse observation, one of the oldest continuous traditions in human culture, with records dating back to Chinese observations in 2136 BCE, would not exist. If the moon vanished, the last total solar eclipse would have already happened. No future generation would ever see the corona with naked eyes. No future child would stand in the moon's shadow and watch the sky go dark in the middle of the day. The phenomenon would pass from experience into history and eventually into legend, and eventually into the kind of distant, half-believed story that the very old tell the very young, who smile politely and cannot quite imagine it. This is what the moon is. It is a gravitational anchor, a tidal engine, an axial gyroscope, a rotational brake, a potential catalyst for the origin of life, a contributor to the magnetic field, a calibrator of orbital cycles, a timekeeper, a navigator's companion, a muse, a deity, a nightlight, and the creator of the most beautiful shadow in the solar system. It is all of these things simultaneously, and it has been all of them for 4.5 billion years, and it will continue to be all of them for as long as the sun allows. And it asks nothing. It makes no sound. It produces no light of its own. It simply orbits 238,900 miles away at 2,288 miles per hour, turning the same face toward us, pulling the same oceans, steadying the same axis, breaking the same spin, holding the same line against the gravitational chaos that would otherwise make this planet uninhabitable. It does this in silence, in vacuum, without awareness, without intention, without any mechanism that could be called purpose. And yet the result, the cumulative result, after 4.5 billion years of silent, purposeless, mechanical fidelity, is everything. Everything you have ever seen, everything you have ever loved, every breath you have ever taken on a planet whose air was kept in place, in part, by the dynamical influence of a world that has no air of its own. If the moon disappeared tonight, you would not feel it in your bones, you would not hear a sound, you would simply look up at some quiet moment between midnight and dawn, and the sky would be wrong. The familiar glow would be absent, the shadows would be deeper, the tides, by morning, would be diminished, and nothing in your experience, nothing in human history, nothing in the memory of any civilization that has ever existed would have prepared you for what that absence actually means, because the moon is the most important thing you have never thought about. It is the foundation beneath the foundation, the condition that enables the conditions, the silent partner in every sunrise, every season, every tide, every breath of wind, every stable century of climate that allowed a forest to grow, or a coral reef to build, or a city to be founded, or a child to be born in a world where the axis does not tumble, the winds do not scream, the oceans do not vanish, and the sky holds its ancient, familiar face from one night to the next. You have lived your entire life in a world shaped by the moon. You have never known anything else. And the measure of the moon's importance is precisely this, that you have never had to think about it, that it has worked so well for so long, so quietly, that its contribution has become invisible. The greatest gifts are always the ones you do not notice until they are gone. The moon is not gone. It is there tonight, as it has been every night for 4.5 billion years, doing what it has always done. Pulling the water, steadying the axis, slowing the spin, guarding the sky. Ask nothing of it. It will ask nothing of you. That is the arrangement. That has always been the arrangement. But the next time you see it, the next time you glance up at the pale, cratered face hanging in the darkness, know what you are looking at. You are looking at the reason this planet works. You are looking at the architect of your world. You are looking at the single most consequential object in the history of life on Earth, and it is so close you could reach out your hand and cover it with your thumb. That is what the moon is. That is what we would lose. And that is why, of all the objects in the sky, this one, this quiet, dead, magnificent, essential one, deserves more than a glance. It deserves your wonder.